Hi everyone, my name is Zhou. I'm very glad here to present our ICLR 21 paper, Hopper multi-hop transformer for spatio-temporal reasoning. Reasoning is the ability to manipulate knowledge entities in terms of relations. Humans are subconsciously performing reasoning all the time. For example, when we are driving, we would first recognize objects, which are the knowledge entities. Then we would form an understanding of relations between these knowledge entities. Similarly, the heart of machine reasoning is having the means for algebraically manipulating previous acquired knowledge in order to answer a new question. We have tons of real applications of reasoning. For tasks like this, we really need a better notion of having knowledge and reasoning, and this is where our current models are lacking. Most current neural networks are just large correlation engines. They can easily be fooled by statistical superior patterns and dataset biases. Therefore, they cannot adapt to our real world, which is constantly changing. In this paper, we address the problem of spatial-temporal object-central reasoning in videos. Specifically, we focus on the problem of object permeance, which is the ability to represent the existence and the trajectory of hidden moving objects. Object permanence can be essential in understanding videos in activities like shopping. One needs to infer what items the shopper should be built for, or driving to infer is there a pedestrian in the front who is going to pass the street, and so on. Answering these questions require the ability to predict the location of non-visible objects as they are occluded, contained, or carried by other objects. Hence, solving this task requires compositional multi-step spatial-temporal reasoning. Under this objective, we were using a synthetic dataset called Cater, which was released at ICLR 20. In Cater, there are different types of objects moving simultaneously. Objects can be occluded, contained, or carried by other objects. Every video has a special object called snitch, and the task is snitch localization. It means we need to find out where the snitch is in the end of the video. We propose Hopper to address object permanence and debias the video reasoning. Before the reasoning step, Hopper first obtains the frame representations and time-ordered object representations, which constitute coarse-grained context information and fine-grained entity information. Then, Hopper uses a multi-hop transformer to perform multi-hop reasoning to reason about object permanence. Humans realize object permanence by identifying keyframes where objects become hidden and reason to predict the motion and the final location of the objects in the video. Given video and a localization query, Hopper used a multi-hop transformer over image and object tracks to automatically identify and hop over critical frames in an iterative fashion to predict the final position of the object of interest. A contrastive debiasing loss is utilized to reduce spatial-temporal biases when training the model. Structure priors such as tension here, which can be treated as a soft tree, are essentially composition rules that provide good and right inductive biases and lead to higher forms of reasoning. Multi-hop transformer is our novel model and contribution for reasoning. It operates in an iterative fashion, and each iteration produces one-hop reasoning by selectively attending to candidate objects. Later iterations are built upon knowledge collected from the previous iterations, and the size of the candidate pool decreases as iteration runs. For snitch localization, multi-hop transformer operates in an autoregressive manner. For example, if hop 1 chose an object in frame 6, then hop 2 can only choose from after frame 6. This is achieved by masking. The hopping ends when the most attended object is an object in the last frame. With a total of edge hops, multi-hop transformer produces refined representation of the video query. As the complexity of video varies, edge should also vary across videos. For example, this video only requires 2 hops, since the last visible snitch is in the second last frame. Several training methods were proposed for the snitch localization task. Notably, Hopper uses a contrastive debiasing loss that enforces consistency between attended objects and correct predictions. This improves model robustness and generalization. We also built a new dataset, Cater Hard, that reduces temporal bias in Cater and requires longer-term reasoning. In Cater, almost 75% of videos have the last visible snitch in the last 2 frames. We released Cater Hard, which is a more difficult video reasoning dataset, to avoid any model to achieve high performance by taking shortcuts to only looking at the last few frames. Our method achieves state-of-the-art accuracy in cater and cater-heart video reasoning and object permanence tasks. In this work, we describe how to perform multi-step reasoning in videos by using iterative reasoning over critical frames. We demonstrate the effectiveness of using a contrastive loss to reduce biases. Based on our results, we also propose a new dataset, cater-heart, that requires longer reasoning hops. In the end, I want to thank my collaborators and also thank you for watching.